Well, good. Well, I've got really great news. I'm the last speaker. The bad news is it'll take a few minutes, but I'll make it as painless as possible. As you probably noticed, it's almost impossible for me to start a presentation without using some quotation. It's kind of in my DNA. So, of course, I had to start with a quote for my own last presentation. So I turned to the great scientist and kind of chronicler of paradigm shifts, C.P. Snow, who said that the problem with getting on the moral escalator is that it's hard to get off. And I think that we're on a petroleum fuel escalator, but I know that we can get off if we all work with great collaboration. So just kind of start with that notion. But what I'm going to end this symposium with is, I think, the view that how we look at renewable methanol going forward. So let me get into that. I think I just want to briefly just touch on some of the underlying greenhouse gas issues and the technology we've looked at. But also get to our vision of low carbon mobility ultimately. I'd like to start with, once again, a quote, but it's a very profound one. It's by the famous scientist Carl Sagan, who simply observed that the Mauna Loa carbon dioxide data is the most famous graph in the history of science. And I believe he said that for several reasons. Of course, the implications of climate change, but it also shows the remarkable organism of Earth, shows us essentially breathing as a planet with that variation, winter to summer variation that you see implicit in that. And of course, that same data is replicated just over our horizon to the Iceland's neighbor in the Summit field station in Greenland, which is similarly measuring global CO2. And of course, that has exceeded 400 ppm just several years ago and is continuing to escalate. So that's really our underlying charge, I think, in large part, that motivated the formation and the continuation of our company. And when I look at CO2 emissions, we know that both in terms of per capita and total emissions, there's a substantial contribution from European countries. This shows a variety of those, but the point is that all of them have an important role to play and have an important share of the problem. The other way to think about mobility, sustainable mobility, is what isn't sustainable. And high performance, the trend to ever increasing uber horsepower, uber torque, uber performance, I think, is not sustainable. And this kind of Prius is not where I think we're heading, but in the other direction. So the way we've looked at this is that we understand that this is a big puzzle. I think of it as a Rubik's Cube. Sometimes you don't realize you're about to solve a Rubik's Cube until you're literally 1 or 2 steps away, and it can look rather daunting, but we do think that we have an important piece to help really solve the issues of stranded and off-peak renewable power storage, along with ultra-high efficiency engines with a liquid fuel that has all the dexterity and efficiency of transportation that other alternatives don't have. Plus a resource base that allows you to essentially convert from a base of oil refining to carbon dioxide refining, if you will. So that's kind of the basic picture, and I know most of you have seen Benedict's excellent presentation yesterday. I won't go into much detail, but the fundamentals, of course, are taking any flue gas, and inherently we're using CO2 twice, essentially. That's the underlying resource and energy efficiency value proposition. And of course, our plant nearby is just one step, one of the first steps along this transition. One of the things that is, I think, most important looking at how this technology rolls out and deploys in higher volume is that it can integrate with a variety of renewable energy sources: solar, wind, hydro, here of course geothermal, biomass gasification. So there's quite a bit of diversity, of course, in terms of renewable energy sources. And then you also look at high CO2 value sources, and we've published papers on steel plants, for example, with Mitsubishi Power Systems Europe. We have an important collaboration with them, in fact. Some of you probably know we have a demonstration plant that's being built in Lunen, Germany, to explore applications from the other power sector. But we also see ammonia plants, cement plants, fossil power plants, as I mentioned about going on in Lunen. So there's a variety of CO2 feedstocks, and of course there's even sources of excess hydrogen. So this is part of a presentation that was integrated in a paper that was done by us along with Mitsubishi Power Systems that suggests that if you take a holistic view and carefully analyze the issues of carbon capture and sequestration, that utilization is really the first low-hanging fruit, and I think that it's a relevant and appropriate comparison or analog. That you think of this as industrial EGR. We've known in the motor vehicle segment that exhaust gas recirculation and energy efficiency in general, but it is starting with EGR. It was one of the bedrocks of energy efficiency, and what we're doing essentially is recirculating gas and converting that gas into a liquid. So of course we're focused on opportunities to find power to hydrogen applications where we help balance the grid and store intermittent power. Right now, batteries are only capable of storing maybe several megawatt hours, maybe up to 10 or 20 if you're really capital intensive. But in a single year, our plant's capacity is capable of essentially storing 50 to 80,000 megawatt hours of product. So storage of methanol and storage of electricity as a chemical is an extremely important pathway. Of course, hydrogen to methanol is what we're doing. Unlike synthetic methane, we require 3 moles of methane, of hydrogen, compared to 4 moles if you went CO2 plus hydrogen to methane. So there again, you've got an inherent some advantage. And of course, the entire emissions to liquid process is something that we have integrated here. So right now, we're looking at, if you really take a longer lens, and then we think it's always important to look over the horizon, because the horizon always comes faster than you can anticipate it seems. But of course, today we're doing geothermal-based electrolysis. We could imagine doing that with a variety of renewable sources, but also getting beyond electrosynthesis into photosynthesis, and breaking those bonds and forming the reaction directly. And there is research going on in that regard, and I think that solar fuel is kind of part of that pathway. Another thing I'd want to iterate, and this came out I think in some of the conversations, and I think we're lucky to have someone here from the global Volvo global truck and transit technology. Volvo did a very impressive analysis several years ago, looking at a variety of alternative fuels and then also a variety of careful full LCA type of analysis, and concluded that DME and methanol both had tremendous high promise. If you look at the details, essentially they came up with the same scores, which were the highest among the alternatives that were looked at. So we know that there's a lot of validation to the direction that we're going. And of course, we've had independent tests done validating our facility. We respect the need for third-party validation, and so through Ameo Carbon Solutions and the ISCC Plus, they've looked carefully and found that our product represents a 90% reduction compared to the baseline gasoline in the European market. So I don't get into those details. I think we also should, of course, always remember that even dating back to the days of California's program, we've had established very clearly that methanol as a molecule inherently has less ozone forming potential. It has a different reaction chemistry And as a result, its reactivity is far less than the olefins, for example, a wide range of products. So you probably know in gasoline there's about 200 separate types of molecules. So that entire complex of the olefins, the aromatics, of course, have a great toxicity, benzene, toluene, xylene, that complex. Another thing to bear in mind thinking about sustainability is that especially as we do try to learn what we need to about the VW experience, and even more recently perhaps Mercedes, that the diesel engine cycle is inherently struggling to meet in-use compliance targets. And if you look, and the reason why those standards are in place for diesel are the fact that diesel particulate is considered a very severe air toxic. And it turns out if you do a careful calculation, looking at benzene, diesel, or formaldehyde, yes, formaldehyde needs to be controlled carefully, and it can be with prudent and careful catalyst selection. But if you look just at the unit risk factors, this is a public health metric, if you will. But it turns out that from the inhalation cancer risk metric, that diesel particulate on a per gram basis, on a microgram in this case, is 50 times more potent risk than formaldehyde, which one would associate with some off-cycle methanol. So looking at this, we think we've got the pieces that are starting to fall into place. You've got the world's first industrial scale CO2 refinery, coupled to the world's first multi-megawatt renewable power to hydrogen to liquid fuel going into transportation pool. You've got the vehicle outside as a step in that direction. You've got the Fiat the prototype that's being demonstrated by Sarah Energy. You've got stations that are again being established in now the second decade of the century. You know, we're continuing on that path. One of the implications that I did want to draw out is, and I'm using a methodology that's not just our assertion, this is mimicking a methodology that Audi utilized when they compared the greenhouse gas well-to-wheel impact of cleaner fuels like ethanol, for example, or advanced biofuels, if you will, cellulosic, and they applied that to their conventional vehicle fleet. The point here is that by taking that 90% reduction as a fuel and using it in a world-class hybrid, and I would assert that the Volvo XC90 plug-in hybrid is probably the most remarkable large SUV hybridized hybridized vehicle out there. By comparison, the Prius, which has been widely praised, and I certainly respect the technology, that has 90 grams per kilometer as a benchmark. The Volvo has been certified at 60. Well, if that Volvo were operating on Vulcanol, it wouldn't be operating at 60, it'd be effectively operating as a 6. So that just shows that long term, if we can get all of these pieces in high volume, that this really becomes, that this meets the 80% target that Mike Jackson referred to earlier today. So I think, again, we're seeing that there are platforms evolving. I don't need to go into this into more detail, but we think that's certainly important. And I did want to add kind of my own personal perspective on this, because I've had, I think, a unique opportunity to be involved with all the alternative fuels, particularly at their early state of gestation. I was involved in programs where we invested the first $1 million into Ballard before they IPO'd, before Ballard became the large fuel cell company they are. I've opened up hydrogen stations to support the hydrogen fleet. I've, of course, operated electric vehicles on test tracks of OEMs, and I've broken down and gotten stranded. That was pre-iPhone days, where there were no phones in the cars. But the point is that it's my fundamental and categorical belief, and it's actually I believe it's a simple statement of fact, is that the only scalable means of transitioning to renewable hydrogen as a means of propelling mass mobility is going to be through renewable methanol. The hydrogen fuel cell vehicles are a short but ultimate dead end. And I say that with all respect to the great technology that's embedded in all those fuel cells that are out there. But the simple fact is that the amount of hydrogen that's being produced with our 6 megawatts annually, the nominal capacity far exceeds the total amount of hydrogen, let alone renewable hydrogen, that's being utilized in the entire global fuel cell fleet. So it's just to remind us that the stations that you hear about that are hydrogen fuel stations have a small fraction of the throughput of the station that Maz referred to, or a conventional gasoline station that Michael showed that were set up in California that we know that can be set up in the future. The point is that 100 kilograms a day is a far cry from the gasoline throughput equivalent that would require 1,000 kilograms an hour. And to produce 1,000 kilograms an hour, you'd need 50 megawatts of power. So the point is that hydrogen infrastructure is an extremely costly proposition. Just to bring a little bit more technical color to that, the capital costs that we're talking about for methanol flexible fuel technology have been publicly stated at $100. 100 to 200 certainly minimum. The infrastructure costs for the kind of stations that we're talking about are roughly $100 to $150,000. That's an equivalent throughput of gasoline. With hydrogen, you're literally talking $60 to $80 million capital proposition per station. If either you're storing a huge amounts of hydrogen or you're producing 50 megawatts worth of that 1,000 kilogram an hour. So it's really, that's why you're not seeing very high, ultra high levels commercially relevant hydrogen station refueling. And of course, the other fascinating fact of chemistry, that is one of the perhaps mysteries of chemistry, is that there is greater hydrogen ion density in a liter of methanol than there is in cryogenic liquid hydrogen. Just the way it is because of the nature of the polarity of the molecule. I don't think I'll get into this because Benedict played a good role in this, I think, in summarizing this. But I did just want to go forward and talk about our low carbon vision, as we see that ultra low carbon intensity renewable methanol can be industrially scaled. We could readily get to 50 megawatt scale, which could easily get to 100. And once you get to 100, why can't you build 100? And why can't you build several hundred of those? It's really quite a scalable opportunity. And then when you look at the vehicles, and the main reason why today's meeting is so key is that as you build up the infrastructure, we will need a very highly efficient vehicle fleet to take full advantage of the methanol value proposition. And once that high efficiencies that we've heard from various researchers today, once that's applied to the vehicle fleet, that energy equivalent ratio really gives you a potential coupled with the comparisons. It gives you a potential to compete with the greenhouse gas impact of fuel cell vehicles. I know Mike Jackson has done some theoretical work in that regard. So those are kind of our long-term vision, but I would say to conclude that I think that we stand at the crossroads of some major breakthroughs. We're making them in real time. One of them is just outside the door here. We appreciate that all the participants here today have a tremendous role to play in realizing the potential of methanol and renewable methanol. And we think forming some kind of a vehicle development alliance would be helpful. And we really welcome everyone's participation, as you see fit. So we do want to sincerely thank everybody for attending and your vigorous participation. So on behalf of CRI and Geely, I want to thank you for just coming. Thank you very much.